You ever wonder how a navigation app picks the fastest route? Or how your email somehow just knows what's spam and what's not? Well, at the heart of it all is a machine that's learned how to make decisions. Today, we're going to pull back that curtain and look at one of the most powerful and honestly one of the most intuitive ways that machines learn to think: the decision tree. Okay, so let's frame this with a little analogy. Picture a detective trying to solve a puzzle. They don't just magically know the answer, right? No, they look at all the clues and they ask a series of questions. Each answer they get guides them, getting them one step closer to the truth. That is exactly what a decision tree does with data. It learns to ask the right questions to solve the puzzle.
So, to build our case, every good detective needs some clues. And for us, that means we need data.
Let's start with a really classic, simple problem. This table here shows us data from 14 different days. It tracks the weather conditions, outlook, temperature, and so on. And then the final decision: did someone play tennis or not? Our mission is to look at this data and cook up a set of rules so that on any new day, we can predict whether it's a yes day for tennis or a no day. Now, this is the really critical first step. Put yourself in the detective shoes. If you could only ask one question to get the biggest possible clue, what would it be? Would you ask about the outlook, the temperature, humidity? See, the machine needs a totally logical way to figure out which of these questions is the most powerful starting point. So how does it find that best question? Well, the machine basically goes on a quest for purity. Now, that might sound a little abstract, but I promise it's a beautifully simple idea. Take a look here. The whole goal is to create groups that are pure. On the left, you see a group where every single answer is yes. There's no confusion, right? Zero disorder. But on the right, you've got an impure group. It's just a messy mix of yes and no answers. So the goal of asking a question is to split our messy, mixed-up data into groups that are as pure as we can possibly get them. You know, in the world of data science, this concept of impurity or randomness, it's got a name: entropy. High entropy means high disorder, like that jumbled up group we just saw. A perfectly pure group, where every single answer is the same, has an entropy of 0. So the machine's goal is to ask questions that drive the entropy of its little data piles all the way down to 0. So for our starting tennis dataset, which has 9 yes decisions and 5 no decisions, the initial entropy is 0.940. Think of that as our starting level of messiness. It's not total chaos, but it's for sure a mixed bag. Okay, so we have a way to measure messiness. Now, let's actually use it to find the best clue. And this brings us to the detective's secret weapon, something called information gain. It's really just a simple calculation. It tells us exactly how much a particular question will reduce the overall entropy, the messiness of our data. So a question with a really high information gain is a fantastic question. It brings a ton of clarity and sorts things out really, really well. So the machine does the math. It calculates the information gain for asking about every single attribute. And the results, well, you can see them on the chart, and they're kind of fascinating. Asking about outlook gives us an information gain of almost 0.25. I mean, look how much higher that is than asking about humidity or wind or temperature. The data is practically screaming at us that outlook is our most powerful first question. And just like that, there we have it. Outlook is our starting point. It has the highest information gain, so it becomes the root, the very top of our decision tree. We found our first and most important question. Now let's actually see how this builds out the rest of the tree. It's pretty cool. So the next logical step is to take our original table of 14 days and just split it up. We'll make smaller piles based on the answer to our big question. And outlook can be sunny, overcast, or rain. First, let's look at the pile for sunny days. This new, smaller table, it still has a mix of yes and no answers. That means the group is still impure. Our detective work isn't done yet. So the algorithm repeats the entire process, calculating entropy, calculating information gain, but only for this little pile of sunny day data to find the next best question. But now, check out the overcast pile. Every single time the outlook was overcast, the decision was yes. This group is totally pure. Its entropy is 0. We have a final answer. This whole branch of the tree is finished, and we've just discovered our first rule: if the outlook is overcast, play tennis. We call this a leaf node. And the rain pile? It's also still a bit mixed. So just like with the sunny group, the algorithm will dive into the smaller dataset and ask, okay, just for these rainy days, What's the best question to ask now? Is it about the wind or maybe the humidity? It just keeps repeating this process until every single branch ends in a pure, decisive answer. And after running this process over and over again, the machine generates this, a set of clear, human-readable rules. This is the insight that it's pulled out of all that raw data. It's not just a table of facts anymore. It's an actual strategy for making a decision. So, we've built the tree, which is really just a fancy set of rules. How does the machine actually use it to make a brand new prediction? To see this in action, let's switch to a totally new problem. Let's imagine a machine has already analyzed this business data and built a decision tree to predict if profit will go up or down. All the hard work of finding the best questions is already done. The tree is built and ready to go. Now a new piece of data comes in. We want to predict the profit for a case where age is mid and computation is yes. It is incredibly simple. We start at the root of the tree, which the algorithm already figured out was age. We follow the mid branch. That leads us to another question, computation. We follow the yes branch, and boom, we hit a leaf node. The prediction is down. And that's it. It's just a game of following the path down the tree. The machine doesn't have to think anymore. It's turned its learning into a lightning-fast flowchart. It has successfully classified new, unseen information based on the patterns it found, all on its own. You know, this quote from Carly Fiorina really captures the essence of what just happened. We started with this simple table of data. By applying the logic of entropy and information gain, the machine turned that data into information, our decision tree, which, in turn, gives us actual, actionable insight. So, decision trees are absolutely fantastic for sorting through nice, neat categories like sunny, rain, yes or no. But what happens when your data isn't so clean? What if you're dealing with temperature readings or stock prices or someone's exact age? How does a tree decide where to split a continuous number? Well, that's a fantastic question and a story for another time.